All right, let's look at 22 questions similar to maybe what you'd see on exam 4. Okay, I wonder how many of these are multiple choice. Quite a few. So I'm thinking just 3 of them to be fill in the blank. All right, so not that that indicates too much. Quite often students will still perform not so great on multiple choice compared with fill in the blank. So you can be sure that you're going to see some indefinite integrals of at least of a polynomial. So sorry, that's so messy. So the indefinite integral of 5x to the 4th minus 3x squared plus 2 with respect to x. Now this is not too hard to do because we have our rule that the integral of x to the n just becomes, I mean, if you can add 1 to n, you can find the antiderivative because it's this new exponent over that exponent. And don't forget your plus a constant. So then our problem right here would just be 5 over, the new exponent is 5, so it's 5 over 5 x to the 5th plus 3 over, or excuse me, minus 3 over 3 x cubed plus, now this is an x to the 0 right here because x to the 0 is 1, so 0 plus 1 is 1. That new exponent is 1. Here's my 2, and then it's divided by 1. All right, and don't forget your plus a constant. Okay, and then there might be just some language that says, hey, here is a function, find its antiderivative. Now to find an antiderivative just means to integrate it, right? So now this is likely not to be a typical polynomial function, but that's okay. You are a calculus student. You will just rewrite this with a rational exponent so that you can apply our rule. The antiderivative of little f should be labeled capital F, and if you can add 1 to a minus 3, you can find the antiderivative. Minus 3 plus 1 is minus 2, so this would be divided by minus 2x to the minus 2, and then of course it is plus a constant, and we get minus 1 over x squared plus a constant. All right, and you can expect most definitely to see something related to doing the method of substitution. When you want to do substitutions, you need to let u, I'm going to say this very informally, let u equal the part of the function that has its derivative somewhere else in the function. what do we mean by that? So if I want to integrate, let's say here's an x squared, and then here in parentheses I have an x cubed plus 1 to the 50th power, then I can see that x cubed plus 1 has a derivative that looks like an x squared, right? So u would have to be x cubed plus 1, because then du would be 3x squared dx, and then you just divide both sides by 3, and then you would have an x squared dx. Or maybe it's you know, the integral of x squared and then 2 to the x cubed, you know, something cute like that. Here, I'll even put a 3 right here, because then if I say let u equal x cubed, then du is 3x squared dx. So this stuff that's underlined is du, and then this thing in the box is u, and you would have a complete substitution. Okay, and then it's something that you know how to find the antiderivative of. And then we'll have to deal with probably some definite integrals, but you would just be looking, so you might see some definite integrals, but be careful, because you're going to want to study the limits of integration carefully so that you can take advantage of any properties of the definite integral that you may see. So I might ask a question like that says, simplify this integral. Don't integrate it, but just simplify it. Well, x squared is an even function, so if I integrate across this symmetric interval of an even function, then really I just need 2 times the integral from 0 to 2 of x squared dx. That would be a simplification. Or maybe I get really silly and say integrate from -2 to -2, and I might do something crazy to you, like give you an antiderivative, or give you a function that has no elementary antiderivative, like this one. No matter how hard you try or how smart you are not going to be able to find this antiderivative. It doesn't exist as an elementary function. You can't write it down. We don't know this antiderivative as of any of the functions that we know. But look at your limits. We're not going anywhere. We're integrating, you have some function, and the limits of your integration are, you didn't go anywhere. There's no area there. The answer is just 0. One of the other properties might have been to integrate from 2 up to -2 of a negative x squared, and I might ask you for a rewriting of this, and you would have to say this is from so you would multiply by a -1 to flip the limits of integration. Those are the same thing. All right. And let's see what else. Keep in mind that the integral of a derivative is that undifferentiated function. And if it has limits, then you can use the fundamental theorem of calculus. So you keep in mind that if I have a derivative function and then I integrate it, I'm going to get back this function. So in particular, where might you see this? Well, what if I have my marginal cost function? Like, I know my marginal cost function through some research, and now I would like to know the cost function. Then we can integrate that cost function. Or excuse me, then we can integrate that marginal cost function to get the cost function. Okay, and let's see, what else might be there? Definitely you would see an initial value problem. An initial value problem is where you are given a you're given the derivative of a function, and you're told one point where the undifferentiated function goes through. You see, because the antiderivative, there's many antiderivatives. There's an infinite number of antiderivatives to this function, because you would integrate, or excuse me, find the antiderivative and then just put a plus c. And since c can be any number, you have an infinite number of these antiderivatives. But as soon as I tell you a particular spot where my antiderivative goes through, then of all of the different, here's an antiderivative, and here's the antiderivative, and here's the antiderivative, and there's a whole vertical stack of them. But as soon as I tell you that it must go through this point, then you just have this one as the antiderivative. So here is f prime. It is this polynomial. Find the antiderivative. Okay, so little f would be, so 4 plus 1 is 5. That's 3/5 x to the 5th. 1 plus 1 is 2. So this is 4 over 2 x squared. Plus a constant. Okay, well, I know that this 4 over 2 is just 2, so let me fix that. Bum, bum, bum. And then we know that f of 1 is 1. So f of 1 would have to be 3/5 times 1 to the 5th plus 2 times 1 squared plus c, and it's got to equal 1. Okay, so that would mean that this is 13/5 plus c is equal to 1, 1 being 5/5. Then you can now calculate c. C would have to be equal to 5/5 minus 13/5. So that would be a negative 8/5. And then you can take that negative 8/5 and replace it right there and have the solution to that initial value problem. You're gonna see probably some Riemann sums. Riemann sums. Remember that the notation for a Riemann sum looks like maybe L4 or R4, where this might mean, or this does mean, make a left Riemann sum of 4 rectangles, or a right Riemann sum of 4 rectangles. and you're going to want to have an idea about when the Riemann sum is an overestimate or an underestimate. So let's think of if I had, let's draw a couple cases here. So if I had an increasing function, that was concave down over some interval, let's say from 1 to, or I'll do from 0 to 2. Here's a function from 0 to 2, and let's do an R4. Okay, and I don't know what the function is, it's just f of x. Okay, I can still write down what R4 is in terms of f. Now it's got to be a right Riemann sum, so that means the right corner, the top right corner of my rectangles will touch the curve. Remember that the width of the rectangle, this is exactly the width of the rectangle, and it is just the length of the interval divided by the number of rectangles. So for us here, that's 2 minus 0 over 4. So that means that each of these rectangle widths are 1/2 right here. And it is a right Riemann sum, so the top right corner will come up and touch the curve. And if you draw this picture, let's suppose the question was like, are you going to have an overestimate or an underestimate? Well, then this would be an overestimate. If it was a left Riemann sum, like here in the blue, it would be an underestimate. Right? Okay, perfect. And these sums can be easily written down because here my width of my rectangles is always 1/2. So each rectangle has an area that looks like 1/2 times the height of the rectangle, and the height of the rectangle is always described by the function itself. So my left Riemann sum would have to be 1/2 times f of 0 plus f of 1 plus f of 2 plus f of 3. And that would be my Riemann sum for a left. That would be a left Riemann sum. Notice it starts with the leftmost endpoint. If I was trying to do a right Riemann sum, I would not start with this first point, because that's not the point that touches the curve. This is the, oh, I screwed up, didn't I? It's not f of 0, 1, 2, 3, 4. It's 0, 1/2, 2/2, 3/2. So this would be, here's how I do it. 0/2, 1/2 plus f of 2/2 plus f of 3/2. Now I've got 4 heights, and then when you distribute, if you distributed this 1/2 right here, you'd have 4 different areas. For a right Riemann sum, you would not start at the leftmost endpoint. You would start at the second one, right? You would start at the second. Let me back up here. Notice that this did not terminate at 4/2. It did not terminate at the 2. We didn't go all the way to the last endpoint for the left Riemann sum. But for the right Riemann sum, you would go all the way to the last endpoint, because you still need 4 heights to get that right Riemann sum. Okay, so what am I saying? I'm saying that R4 would be the width of the rectangles times f of 1/2 plus f of 2/2 plus f of 3/2 plus f of 4/2. And now I've got four heights. And that's how I do my Riemann sums. Okay, we need to understand pretty well the fundamental theorem of calculus. If you're given, so if you're told that there's some antiderivative and you don't know what that antiderivative is, but like there's a table where maybe we can have a table of values, like here's some x values and here's some f of x values. This is one way to talk about a function, 1, 2, 3, 4, and this might be 2, 8, 16, 3. Okay, then there's my there's some values for my antiderivative, and then I might ask you about, well, what's the integral from 2 to 3 of little f of x dx, provided that we knew, supposing that f prime of x equaled little f, capital F prime equaled little f. So then that means you can invoke the fundamental theorem of fundamental theorem of calculus. This would be capital F of 3 minus capital F of 2, and the answer would just be 8. Let's see what else. One property of integrals definite integrals I forgot about was, if you had, like, let's say the integral from 1 to 3 of f of x. Remember that you can take a pit stop somewhere in here at some point that's between your original limits of integration, and then pick back right up where you started and keep going to the end. Like, these are the same because we had a pit stop at 2 and just kept right on going from 1 to 3. Those are equivalent. What else might you see? There's the classic, I guess just some more properties. So the integral of 3x squared plus 4x to the 4th dx, you're needing to keep in mind what our rules were for doing this. We don't explicitly have a antiderivative rule for a function like 3x squared. What we do have is, and we definitely don't have an antiderivative rule for this polynomial, but what we had was that you could integrate term by term. So if you had to break it down for somebody and explain exactly where all this was coming from, you would need to say, I'm integrating term by term, and then the constants can come out in front of the integral symbol. And now when you have it broke down like this, all of a sudden you really are integrating something that precisely follows that x to the n rule that we have. Because remember, for integration, you don't have many rules at all. You have the x to the n rule that says this antiderivative is x to the n plus 1 over n plus 1. You have that. You can probably write down that a separate rule would be, if you had e to the kx, that this is just e to the kx over, well, we can do this more generally, right? We can say, instead of just kx, we can say that this is e to some function where the function is in the exponent. And even though I can do it even more generally than that, I don't even have to have it be e, I can have it be any number at all. This must be the antiderivative, because if you took the derivative of this, you would just get e to the f of x. And so to make this even more general, it doesn't have to be e, it can be any constant. Well, no, I better change that, because then you need natural log. I don't want to talk about that. So we'll just leave it at e. And if it's neither of those, then you have to do a substitution. You would have to do a substitution until it looked like either one of these. And then you could find the antiderivative. Something that was pretty neat that you would have studied was average value of a function. So, you have some function here, makes a graph, and and you want to talk about its antiderivative. Let me do it different. You want to talk about its antiderivative from a to b. Then this area right here, that area, consider that area. Then there is some value here, call it c. There is some value c such that the rectangle of height c and width b minus a, so b minus a is this width right here, and the height is c. There's some rectangle that has the same area as that antiderivative, or excuse me, as that interval. And okay, then, so to find that value c, just divide both sides by b minus a. So then c would be 1 over b minus a, integral from a to b, f of x dx. And that's the average value of the function. Excuse me. What else might we see? Area between curves. For area between curves, just remember it's the top curve minus the bottom curve. Hello? Sorry, my phone was ringing. All right, so area between curves, you integrate the top curve minus the bottom curve. Easy enough. And I guess we are almost finished here. You can use that in a couple different ways. Maybe you had, let me see, let me make a drawing. So here is a function, and there's my x-axis, and so maybe this, this is just some function, and let's say I have a line coming like this, and this point where they intersect right here is, I don't know, how about the point 3 and -5. All right. And so what if you wanted this area here? What if I wanted that signed area right here? Okay, and this line is represented by L of x. Write down the integrals that do it. Okay, no problem. Well, if I were to just integrate, I guess I need to tell you what these limits are as well. So maybe this is -1, 1, and no, not 3, 4. Okay, then if I were to integrate from -1 to 4 of f of x, I would get a negative number that represented all of this. So if I stick a minus in front of it, I'll get the signed area. And I will deduct from that positive number. This is a positive number right here. I would deduct from that this area that's just right in here, and I'd be left with the yellow shaded area. And so that would have to be the integral of from 1 to 3 of just that line L of x, but it's under the axis, so I'll make it negative, and then I'd have to add to that the integral from 3 to 4 of f of x. Now that's just one way to do it. There would be another way. You could say, you could use your top minus your bottom idea, where after the x value of 1, you have a top curve and you have a bottom curve. So you could integrate from -1 to 1. Now watch this. between -1 and 1, what's our top curve here? Well, it's this function 0. This is the x-axis, so the x-axis is the 0 function. So it'd be the 0 function minus the bottom curve, which is f of x. And look how it puts your negative in there for you, right? You don't end up forgetting it. And so that integral would be this part, and then you'd have to add to it. So there's a positive number, and you'd add to it the integral from 1 to 4 of the top curve minus the bottom curve. And then this is also a positive number. And we talked about some applications. In particular, the Gini index is a fantastic application. It was 2 times the integral from 0 to 1 of x minus f of x. All right. And maybe the function that describes this economy is f of x equals to x to the 3.1. Then find that country's Gini index. So you would say integral from 2 times the integral from 0 to 1 of x minus x to the 3.1 dx. And if you can add 1 to those exponents, then you know the antiderivative. So that would be 1/2 x squared minus x to the 4.1 over 4.1 evaluated between 0 and 1. And we are ever so lucky here to have just what looks like polynomials, because when we drop in the 0, those terms are gone. So this would be equal to 2 times the integral of 1/2 minus 1 over 4.1. And if I were to distribute the 2, I would just get 1 minus 2 over 4.1, and you can get out your calculator here, or you can do whatever. So this would be 4.1 minus 2 over 4.1, and you get 21 over 41, which is 0.5129. Okay. And remembering that the lower the number, the more fair the economy is. All right, and beyond that, make sure you know your producer surplus and consumer surplus. The formulas for those are given to you on the exam, so you don't have to remember them. And make sure you know how to use your continuous income stream formula. Continuous income stream, and your present value and future value formulas. And I guess that's it. So, good luck. Talk to you later.